this segment of lectures, we are looking at normal stress differences and stress growth in materials. Earlier we have seen the oscillatory shear, stress relaxation, creep of viscoelastic materials, and we saw that many of these characteristics were useful in the linear range or as a marker of linear viscoelastic response. And elasticity in fluids is an important indicator for understanding the overall behavior of materials, and therefore normal stress differences and stress growth, which are generally observed under large deformations, are very important. So, what we saw last time was an example from macromolecules under shear, and we motivated the presence of normal stresses in macromolecules under shear, and then we looked at a simple model which could predict the normal stress difference, which is non-zero, because all the linear viscoelastic models as well as all the viscous models, whether linear or nonlinear viscous models, would all predict the normal stress differences to be 0. And then we motivated the stress growth response through a colloidal dispersion under shear, and in this segment of the course we will see how do we define material function based on stress growth experiments and look at the colloidal dispersion under shear. So, we looked at the idea that clusters actually break when we have shearing, and the particles can be thought of as bonded to each other because of the attraction between particles, and when shear is applied, the bonds between these particles can stretch and then break under some conditions. So, therefore, this is the underlying phenomenon which is influential in determining the overall rheological response of such network of clusters. And so, if we think of these bonds with a certain lifetime, the fact that there are continuous thermal motions which are going on in this system, and particles in general are vibrating, rotating, translating around their around their positions. So, in that case, based on the thermal motion and depending on its magnitude with respect to the attractive interaction between the particles, the bond may be present or the bond may break over as a function of time. And so, in that case, the transition between these will purely depend on what is the relationship between the attractive potential between the particles and the thermal energy which is present for the particles to move away from each other. So, in such a scenario, we could model the material as a Maxwell model with the relaxation time indicating what is the lifetime of such bonds. And so, in such case, if we look at the material under constant strain rate, and so all of these experiments are when the strain rate is constant, and so we take a cluster of particles and apply a constant strain rate, so that a linear velocity profile basically makes some of the particles to move faster than other set of particles. And so, given a constant strain rate, the Maxwell model reduces to an ordinary differential equation, and the solution of this is an exponential solution. And the solution can be examined under two limits, that when time t is equal to 0, when we have so the stress is basically related to the coefficient eta times gamma dot yx naught, the applied strain rate, and 1 minus exponential minus t by lambda. And given that this is the overall response of the material, you could look at this under two extreme conditions. When time t is equal to 0, the exponential function is very small, and therefore, one can write this as eta gamma dot yx 1 minus t by lambda, and therefore, this will be nothing but eta gamma dot yx t by lambda. or in other word, given that eta by lambda is g, it is g times time. So, that is what is for short time the behavior is where the stress increases linearly, and in fact gamma dot y x, if the deformation is small, is directly related to the strain itself. And so, therefore, what we have is an elastic response, and so at very short time scales the stress increases linearly, or it increases linearly with strain. So, this is the elastic response. Under these type of conditions with very small time imposed, what we have is basically the time scale is short enough that each of these bond actually is formed, and the time scales involved are such that the thermal motion of the particles which leads to the bonds being broken is much slower, and therefore, it would appear at very short time scale that each of the bond exists, and therefore, the material pretty much responds like an elastic solid. Now, if you look at the other extreme, or where the time is extremely large, in this case what happens is the lifetime of bond is defined by lambda, and since we are now looking at time which is very large, in such cases basically the exponential function will reduce to 0, and therefore, tau y x as a function of time will reduce to eta times gamma dot y x. And so, this is a Newtonian fluid response, and in this case tau y x as a function of time will be just a constant value, because gamma dot y x is fixed. So, in this case the picturization of the colloidal system is in this state. So, that basically the time scale given is so large that on an average the particles, rather than remaining bonded to each other, are free from each other. So, therefore, the system behaves as if it is a colloidal particles which are free to move without the bonds, and therefore, we predominantly observe a viscous response. So, therefore, Maxwell model can capture this viscoelastic response, which can generally be observed for a variety of large class of viscoelastic materials, and that will be basically an increase in stress at shorter times and then a constant stress after some time. So, generally for large classes of viscoelastic materials, you would see a response where there is a stress growth, and so this can be used to define a material function which we will call stress growth viscosity. The idea here is to say that given that we are applying a fixed strain rate, the ratio of the stress which is being measured to the fixed strain rate which is being applied is defined as the stress growth viscosity, and since the stress itself is a function of time, the viscosity also is a function of time. So, based on this we can define a material function which is stress growth viscosity. It is a material function which is being measured at constant strain rate in a simple shear flow. At time t is equal to 0, a constant strain rate is applied, and in this case we are writing the strain rate for a cone and plate device, in which case theta phi or phi theta are the only non-zero components, and then we measure tau theta phi as a function of time, and the stress growth viscosity is defined as the ratio of the stress which is being measured divided by the strain rate which was applied, and this material function is a function of time. So, similar to the other material functions which we defined, for example, viscosity itself was a function of strain rate. Many of the oscillatory material functions were functions of frequency, and therefore, we have now another material function which is stress growth viscosity, which is a function of time. If you recall, the relaxation modulus was also a function of time, and similarly the creep compliance was also a function of time. So, stress growth viscosity, given that it contains response of the material in the elastic limit as well as in the viscous limit, is a good indicator of viscoelastic response, and this increase and at what times would the elastic or viscous response be observed will depend on the relaxation time. So, similar to many other material functions that we saw, that under two extreme conditions they either show viscous or elastic response. Given that we are looking at Maxwell model, in stress growth also we can see the two extreme responses. Otherwise, the overall stress growth viscosity for Maxwell model is an exponential function. So, now in case of material where the clusters can break down, but they have a finite time of breaking, and there is the strength of these attractions is reasonably high, so that certain amount of shear is required, and only then this breaking can happen. The Maxwell model response we interpreted in terms of thermal fluctuations overcoming the attractions, and therefore, these bonds could be broken only due to the thermal motions. But if these attractions are strong enough, then what happens is the thermal motions are not sufficient to break these bonds, and a degree of shearing is also required for the stretching and breaking. So, therefore, stretching and breaking of bonds is possible in addition to thermal motion being there, shear is must, and only then this can happen. Of course, in all cases the reverse reaction can also happen. Earlier we saw with Maxwell model interpretation that given that the particle will fluctuate, move around, it can again bond back, and therefore, the bond is again formed. Similarly, in case of shear breaking these bonds, if shear is removed, then particles can again move and form the bond, and again the network of clusters can be formed. So, many of the colloidal systems will undergo this change in microstructure from a network of clusters to broken clusters, and this is mediated by shear. So, in such cases a simple model which can be used to describe the behavior of response is called a structural model parab. So, there is a structural model through a structural parameter which is indicated as SP here is used. Now, what we are trying to do here is to say that whatever is the microstructure of the material that can be indicated and captured using a parameter. So, microstructure of a material which in our case is based on the number of bonds between particles, and this changes as a function of time. And we know that it forms and breaks. So, break happens because of shearing with a given rate, and then formation happens that because the thermal motion again lead the particles to approach each other, and so due to thermal motion the formation can happen. So, therefore, in this case the idea is to capture the variation of the microstructure through a structural parameter. So, we make a hypothesis in such cases of a structural parameter, and clearly this structural parameter will in some way is a measure of number of bonds between particles. So, with shearing SP would decrease, and at rest, that is after shearing, SP would increase. So, clearly there is an evolution of SP, and so we need to understand the material behavior, we need to be able to write an evolution equation for SP. And this needs to be combined with a hypothesis of how the number of bonds actually influence the material behavior. So, in the example that I am showing here, the Maxwell model itself is chosen to represent the overall material response. However, the Maxwell model parameters are assumed to be dependent on the number of bonds which are present. Given that the time scales of bond formation and breakage are very significantly influenced by shear, we have to make an hypothesis that under shearing whenever structural parameter changes, the overall relaxation time of the material changes, and the parameter which signifies the viscous response may also change with structural parameter. So, now this is a Maxwell model where the model parameters are functions of structural parameter, and then the evolution of structural parameter itself is written as a differential equation with terms which signify formation as well as breakage. So, when SP is 0, we imply completely broken structure, and we should remember that this is only a measure and some representation of what is the microstructure. Therefore, broken and formed should be viewed as representing and not being completely measurable directly. Formed microstructure. So, there is a rate of change of the parameter, and of course, if all the bonds are formed, which means SP is high, then what will happen is this rate will be higher. So, this rate will be directly proportional to SP, but this will be a rate of breakage. So, more SP is, the more breakage is possible, because if bonds are completely broken and SP is 0, then the rate of change of SP will be also 0. If SP is 1, then the rate of change of SP will be very high. Similarly, dSP by dt will also be related to 1 minus SP, but in terms of formation. If SP is 0, then the formation can happen at maximum rate. When SP is 1, all the bonds are already formed, so therefore, formation rate will be 0. So, this signifies the formation rate, and this signifies the breakage rate. So, therefore, the overall equation for evolution of SP can be written as a differential equation in including two terms. The breakage rate, as we have been saying, is also strongly dependent on the shearing. In the absence of shearing, there is no breakage, and in that case the material will go to SP equal to 1, when finally even the formation rate will go to 0. In the absence of formation, you will only have breakage, and in that case there is no reverting back to the cluster that was there. So, therefore, we have both the formation and breakage term. The rate constant A and C signify how fast or slow the formation and breakage rate are. So, these two equations together govern the response of material, and this is an example of a structural model, because a structural parameter is being incorporated into a constitutive model, which we have already been seeing many times. We have seen that the response of this model alone, if lambda and eta are constant for stress growth, was just an exponential function. Now, given that the parameters themselves also depend on the structural parameter, what happens is these lambda and eta also evolve as a function of time when a constant strain rate is applied. So, when you apply a constant strain rate, that leads to a constant rate of breakage in terms of C and gamma dot being constant, but SP itself evolves, and the evolution of SP will eventually lead to again a steady state. So, in general, what you would have when shear is applied on the material is the fact that dSP by dt will change with application of shear. And a steady state will be reached, steady state is reached when of course dSP dt is 0. What we have is the formation and the breakage rate are same. So, therefore, the A 1 minus SP is same as C SP gamma dot Yx, and clearly so the different steady state will be reached when you have a different gamma dot. So, this equation can be solved to find out what is the steady state value of SP. So, based on this one can get to know what is the steady state value of SP. So, we have basically A minus A times SP is same as C SP gamma dot y x naught, and clubbing them together we have A is equal to C gamma dot y x plus A times SP, and therefore, SP is A divided by C gamma dot y x plus A. So, the steady state value of the structural parameter would depend on how much is the strain rate that is being applied and what are the kinetic constants. If no strain is applied, gamma dot y x is 0, then in that case if gamma dot y x is 0, then we have basically SP tending to 1, A by A which is 1, and if gamma dot y x is very large, if the value of gamma dot y x is very large, then of course we have the completely broken structure and steady state value of SP is 0. So, therefore, the SP actually evolves as a function of time, and so the response also is that even lambda and eta vary as a function of time. So, the overall response of this model to stress growth is given here. We have already seen that the Maxwell model there is an exponential increase and a steady state is reached. We had seen that this response was elastic response, while the overall constancy of the stress growth viscosity is the viscous response at long times. Because of the structural parameter initially being 1 when all the bonds are formed, and then because of shearing there is an evolution and change in structural parameter and a steady value which is reached at long times. So, basically structural parameter decreases, and just to remind us that the structural parameter decreasing is because of the bonds, the average number of bonds which are broken is higher and higher as the time goes on. However, at steady state the average number of bonds remains same, because the rate of formation and rate of breakage are same. And so, in this scenario therefore, initial response at short times is again related to the number of bonds being basically same as the sample at rest, and so completely elastic response, and then at very large times since the number of bonds is less but again remains constant, we again see an overall long time response which is viscous. However, in between the material shows a stress overshoot. So, compared to earlier where we had seen the tau xy as varying monotonically and an increase and then becoming constant, now what we are seeing is an overshoot and then it becoming constant. And so, this is a stress growth with overshoot. And this value, given that this is a constant, so this is the stress overshoot. And clearly what happens in this case is because the value of SP would change depending on what is the strain rate there, as we have seen that the not only steady value of structural parameter, but even the evolution of structural parameter would depend on strain rate. Clearly the response of the model would depend on what is the strain rate, because the evolution of SP is a function of strain rate. So, at different strain rates we would observe that there may be different responses. So, for example, you may see responses like this depending on the different strain rate that is being imposed. So, therefore, now stress growth in these cases is a function of time and also the strain rate. It is a function of time, which was the earlier case also, and also strain rate. So, many of the nonlinear response of materials is according to what we have discussed so far, that at very low strain rates where deformations are small, we would observe stress growth to be monotonic, but as the strain rate is increasing, in higher strain rate is applied, a stress overshoot is observed, and usually the stress overshoot is higher and higher when strain rate is higher. Of course, the steady value of stress may depend on what is the overall magnitude of strain rate being applied, and in fact in the drawing here what we should in fact look at is the fact that each of the stress value that you will get will be higher than the previous one, as the stress will be higher, but the viscosity may be lower. So, at higher and higher strain rates, we will have stress to be higher. However, if I plot the data for the ratio of the stress and gamma dot yx which is being applied, then at a different function of as a function of strain rates, we will get response that I have drawn erroneously earlier as stress response. And in fact, so this is again increasing strain rate, and the fact that the steady value of viscosity is so steady viscosity is lower for a higher strain rate in the example that I have drawn here. So, therefore, what is being drawn here is for a shear thinning material, but the shear thinning is described based on only the steady behavior. However, the stress overshoot describes the unsteady or transient behavior. So, we can define the stress growth material function, which is again the stress growth viscosity, but it is a function of both time and the gamma dot. So, we have now two versions of the same material function, one which is defined for linear response where it is only a function of time, and then we have another function which is called stress growth viscosity again. Only thing is this is being used for a nonlinear response of materials, and therefore, the viscosity is a function of time as well as strain rate. So, in summary, we have seen two important material functions, normal stress differences and stress growth viscosity, both of which are very useful in understanding the nonlinear response of viscoelastic materials.